So there are three types of eclipses you should be aware of. One is a total solar eclipse. That's what happened this past April. And if you were lucky enough to be in this band of totality right there, you might have had the opportunity to see this, where the moon's disk is entirely covering the sun's chromosphere, and all you can see is the corona. Then you have the case of a partial eclipse where the moon is only partially covering the sun. And so if you were anywhere else outside of this total eclipse path, you would have had the chance to see this. And then there's an annular eclipse, which is very much like a total eclipse, except the moon, when it's orbiting Earth, it's not always at the same distance. Sometimes it's closer to the Earth at perigee, sometimes it's farther away from the Earth at apogee. And when it's farther away from the Earth, the moon looks smaller in the sky and can actually fit inside of the sun. So they sometimes call this a ring of fire eclipse. And that's what happened October 14th, 2023. So here are some movies I made that show the paths of these. And these movies are showing not just the path of totality and annularity, but it's actually showing the percentage of obscuration. So you can see really the entire, for the October eclipse, and almost all of the continental United States and a good part of South America had some eclipse. And my friend and collaborator, Dr. Joseph Huba, at Syntec Technologies, he runs an ionospheric model called SAMI-3, where he took the inputs of that movie, put it into his ionospheric model, and he gave us a prediction of how that eclipse would affect the electron count in the ionosphere. And we did this same thing for the total eclipse in April. So here the eclipse is going from south to north. And here's the ionosphere for that same period. So blues mean a decrease, blues and blacks are a decrease in ionospheric electron density, and then yellows and reds mean an increase. You can see some funky things happening down up and above and below the magnetic equator. Those are likely tied to the equatorial ionospheric anomalies. And so you can take those model outputs and you can actually do a ray trace where you predict how an HF radio wave will behave going through that particular ionosphere. So this is a model that we ran from the 2017 total solar eclipse, going from Alpha Alpha 2 Mike Foxtrot to Whiskey Echo 9 Victor in Wisconsin on 20 meters. And here you can see at the beginning of this, let's go back to the beginning of this. Before the eclipse starts, the ionosphere is fairly strong, and Florida can communicate with Wisconsin. As the eclipse goes on, the path gets weaker, the band shuts down, the rays escape into space, the eclipse ends, things recover. So we're able to do this sort of modeling to understand what we're seeing. So we ran something called the Solar Eclipse QSO Party back during the great total solar eclipse of 2017. And then when we saw that these new eclipses were coming in 2023 and 2024, we said this is an opportunity we cannot miss. So we decided to go even bigger. And our HamSCI group, collectively, we came up with this idea of the HamSCI Festivals of Eclipse Ionospheric Science. We had not just the Solar Eclipse QSO Party, but many different experiments taking place. And we have a number of questions. I will tell you what these questions are, science questions. I am not going to answer all of them today. We're still working on analyzing the data, but these are some of our guiding questions. Can the annular eclipse be observed in HF communications? How large is the disturbance? How long before and after maximum eclipse are eclipse effects observed? Is there an onset recovery asymmetry observed? Do we see what what layers or regions of the ionosphere do each of the bands refract off of? How similar are the eclipse effects to dawn and dusk? Now, before I get into the results, I want to tell you about a brand new radio station, ham radio station, that we got to operate the total solar eclipse QSO party from. So I'm a professor at the University of Scranton in Scranton, Pennsylvania, and this is our campus in downtown Scranton, Pennsylvania. It's a Jesuit university with about 5,000 students, and we just had a brand new amateur radio station installed this past November, and it's absolutely beautiful. We have an ICOM 7610 and 7300. DX Engineering was kind enough to give us an ACOM 1010 amplifier. We have ICOM 9700 for satellite and Yaesu 400Ds for local VHF, UHF. We have a repeater, a 440 repeater. And all of this was thanks to a very generous grant from ARDC, almost $200,000, another $20,000 from private donors, and also support from NSF, DX Engineering, and Jeff DiPolo, WN3A. And this is all professionally designed and installed by Broadcast Sciences, Jeff DiPolo, WN3A. So this is our club president, Gerard Piccini, in the station. This is the building. So you can see there, that's where the club station is. You can imagine the view from that room looking over downtown Scranton. It is a gorgeous station. Here's our HF tower. So there's our 40-foot tower on top of a 5-story building with Jim Breakall, Skyhawk antenna, and and our repeaters up there too. We've got our satellite stations here. Absolutely beautiful. So we did get to operate this during the April eclipse. And now let's see if all this, here we go.
Students in Lackawanna County are learning more about radio waves and their connection to the atmosphere and to space.
It's part of a large research project at the University of Scranton. Newswatch 16's Emily Kress tells us more about how the eclipse can change how those waves work.
It's an all-day affair at the University of Scranton preparing for the total solar eclipse. While some students are just watching, others are working hard on research.
Yeah. That's a lot of velocity change.
We're looking to see how this particular eclipse affects the ionosphere and the upper atmosphere. Every single eclipse is a little bit different, going through a different path.
Dr. Nathaniel Frissell is an associate professor of physics and engineering at the university. He says this research has been years in the making. Last fall, the university installed this tower to get a student ham radio station up and running at the Loyola Science Center. Students and other community members are able to connect with people across the country and the world.
When the eclipse comes through, it cuts off the sun and that photoionization, and so now the radio waves aren't bent the same way. And so when you receive the signals on the other end, or you don't receive the signals on the other end, if you look at things correctly, that can be attributed back to the eclipse.
Research like this is important because if we can understand how radio propagation works, we'd be better suited in cases like an emergency where, processes such as, phone lines or any other electronic communication wouldn't really work.
Students spent all day in the ham radio station since other parts of the world experienced the eclipse long before the eclipse reaches our area. The university was one of 5 chosen as part of a citizen science project with NASA. Through this research, students are helping to document history.
It's a pretty cool experience. It's like the environment and how everything is, all the people around here. It's very interesting to see all play out.
That feels pretty great, knowing that we're at the front of this, and would not have expected to have this great opportunity when I first came to the university.
Students will now spend their time breaking down all of the data collected. Emily Kress, Newswatch 16, Scranton.
So it was a really, really great experience being able to use that station. So some of the experiments, I've got 7 listed here. We have the Solar Eclipse QSO Party, the Gladstone Signal Spying Challenge, the Grape HF Doppler Experiment, the Whisper Demon Observations, the HF Time Difference of Arrival Experiment, the Medium Wave AM Doppler Experiment, and the Very Low Frequency and Low Frequency Experiments. And there were probably more going on. I know Case Western had yet another experiment going on. So one of the philosophies at HamSCI is that if someone wants to try doing an experiment, we try to figure out a way to support them and get them in. So we have all these different people doing all these different observations. So here's a solar eclipse QSO party. This one's the most contest-like. It has rules that read almost like a standard contest. You can use N1MM plus and to log it. So you get 2 points for CW or digital, 1 point for phone. You multiply your score by the number of grid squares, and you have an exchange. You submit your logs, but we also use additional data sources, the reverse beacon network that's automatically monitoring the CW traffic, PSK reporter, WhisperNet, participant support logs. That all gives us data for our observations. We've had 3 of these so far, the one in 2017, the one on October 14th, 2023, and the one on April 8th, 2024. And a recap of what happened in 2017, we had a total of, each network provided over 600,000 spots from RBN and WhisperNet, 1.2 million from PSK Reporter, and almost 30,000 QSOs in the participant logs. And we got beautiful results. I only ever analyzed the RBN data from the 2017 eclipse. But even doing that, this is the RBN data. We got fantastic results from that. Up on top here, this is the observations on 14 megahertz for the 2017 RBN solar eclipse QSO party. Right at 0, this is when it was maximum eclipse. This all the way to the left, minus 1.5, that's an hour and a half before the eclipse. All the way to the right, that's an hour and a half after the eclipse. The y-axis is distance between transmitter and receiver, and you can see that the white curve here is the amount of eclipse obscuration present. And so you can see on 14 megahertz, the band was going gangbusters an hour and a half to about 45 minutes before the eclipse, and then it shut down as the ionosphere got weak and the signals escaped into space. And then it recovered. And we were able to model this using ray tracing and that SAME3 output that I showed you before. And we did this on multiple bands. So we were able to do this on 14 megahertz, 7 megahertz, 3.5, 1.8 megahertz. And you can see each band behaves a little bit differently. The observations are on the left here. So we talked about how 14 megahertz shut down. 40 meters, 7 megahertz went long during the eclipse. 3.5 and 1.8, they opened up, presumably because the D region absorption went away during the eclipse. We were able to model this as well, and from our models, we were actually able to tell whether the refractions are mostly from the E region and low takeoff angles, like for 14 megahertz, or from the F region for the other bands. So we don't have these, we are working on doing this sort of modeling for the current eclipses. We don't quite have this level yet, but we are working on it. But we do have some data that we can show you that is really beautiful. We also had the Gladstone Signal Spotting Challenge. This is a contest for people who operate skimmers. It's named for the PSK reporter, founder, and operator Philip Gladstone, November 1 Delta, Quebec. And so we, again, had rules for that. And the basic rules were there were 2 operating categories, transmitters and receivers. You could enter one or both. And the primary modes were Whisper and FST4W. And this was a no logging contest. All you had to do was fill out the form, and then we would go find the data for you. We just go up to WhisperNet or PSK Reporter. We'd download the data, see who entered the contest, and we could tell you who won. And Gary McKeaton and Adarsh and Cam, W7CAM, they are all on the scoring committee, and they started processing this data. So we had 68 entrants from 12 countries there, and these are the spots received and generated just from the people who filled out our form and entered. And here's our submitted log data. If you come to our HamSCI forum at 3:55 p.m. in Forum Room 2, you'll get to hear Gary AFAA talk more about the results, the contesting results from this. But this, doing this solar eclipse QSO party, we've been working on this for a while. We started doing weekly Zoom calls in September 2022, and we have a team that worked on finalizing the rules, developing websites, coming here to Hamvention, having in-person meetings, all sorts of things, print magazines, all to make sure we could get up to this day where we could present some results. So again, come to the HamSCI workshop for the contest results for the 2023 SDQP. So thanks to the people working behind the scenes on this, Gary McKeaton, AFAA, Ed F. Check, WX2R, Mackenzie Denton, KO4GLN, Bruce Horn, WA7BNM, and the Worldwide Radio Operators Foundation, Adarsh Pashakanti, KN6VIS, Cam Cameron, W7CM, and the ARRL for helping with partnering and promotion. And now here's really the beautiful plot. This is from the Total Solar Eclipse Day, April 8th, 2024. This is all of the RBN, WhisperNet, and PSK reporter spots put together. So there's over 52.7 million data points that went into this plot, split up by band. And this is just a summary plot, so we really didn't do any hard work analyzing this, but the total solar eclipse, you could see really obviously opened up the 1.8, 3.5, and 7 megahertz bands. And I'm very confident that when we actually do dive into the data more deeply, we will actually be able to see the upper bands shut down as well. And you can see a little bite out here on 10 meters. But it just absolutely beautiful data. So that was not the only experiment we ran. We also had the Personal Space Weather Station experiment, GRAPE HF Doppler experiment. Now the idea here is how many people know that WWV in Colorado is tied into atomic clock frequency references and is supposed to transmit on extremely stable, provide an extremely stable frequency reference. Great. How many people here know that if you actually listen to WWV with your receiver and you also happen to have a very stable frequency reference, you will see WWV's frequency vary? It does. Okay? So when you listen to WWV pretty much anywhere that's not right next to it, you will see routine variations on WWV's signal. And the reason for that is not because WWV is not stable, and it's not necessarily because your receiver is not stable, although you really need to make sure you have something like a GPS disciplined oscillator to make sure it's stable. What's probably happening is the ionosphere is varying. It's changing the path lengths and the time it takes, the signal to get from one place to another. So you get Doppler shifts. So like if the ionosphere were to move up, that would cause a path length increase, and that would cause the received frequency to decrease and give you a redshift. If the path length gets shorter, like the ionosphere builds up and gets closer to Earth, you'll get a positive Doppler shift or a blue shift, and the received frequency will increase. And so we now have these radio systems that, thanks to GPS disciplined oscillators, and these are little radio receivers that listen to the GPS network. They don't necessarily tell you where you're located, but they're able to provide an extremely accurate frequency reference. We can use that to discipline local receivers that can make very accurate measurements. And Case Western Reserve developed the GRAPE 1 and GRAPE 2, and John Gibbons did a fantastic job on this and got all of these deployed for the eclipses, and we also now have from Whisper Demon and the Tapper group this software-defined radio version that can listen to 9 frequencies all at the same time using RX888 hardware. And here are just some of the people that were behind all of this. We had this New England Grape group. Here's Gary, AFAA, who led the distribution. These are just a few of the people who helped out. Here's all of the data from these systems get sent to a central database run by the University of Alabama. Bill Engelke, AB4EJ, who I met here at Hamvention a number of years ago. We've become good friends and collaborators, and we're still working together today. So this is what the Personal Space Weather Station looked like for the October 2023 eclipse. And then here's what it looked like essentially today. And we had well over 100 of these GRAPE HF receivers. I think there's over 140 locations that we have some sort of Personal Space Weather Station instrument deployed. And so here's some example of that. This is from the New England Grape group that I showed you a photo of before during the annular eclipse on October 14th. So they're located in New England, and they're listening to 10 megahertz WWV. Over here is nighttime. You can see some oscillations up and down. Those could be traveling ionospheric disturbances. You see a big increase in Doppler shift here. So this is going up to 1.5 hertz above the 10 megahertz carrier of WWV. And so that's tied in with the dawn, the ionosphere building up at dawn. So then things stabilize. And then over here, this is where the eclipse happened. So the eclipse is like dusk, then dawn. So you see a negative Doppler shift, then a positive Doppler shift, and then it recovers. And so you can see all these stations from New England basically moved at the same time. The one that's kind of out of place there is actually up in Canada. And so you can get some really nice geographical localization of these measurements. At my house, I also ran another system that could provide additional spectrograms. So instead of just a single measurement per unit time giving you these line traces, you can actually get a spectrum. So my house, W2NAF, is located here near Scranton, Pennsylvania, and I was able to listen to WWV and CHU, and here you can see where the annular eclipse path is, and here you can see where the total eclipse path is and how it crossed these stations. So for the annular eclipse on 10 megahertz, I was just running one of these grape receivers on a single 10 megahertz band, and here's the spectrum. Here's night, here's dawn, and there's the eclipse signature. Absolutely beautiful. And when you look at the data in this spectrogram format, you can actually start to see multipath from multiple layers of the ionosphere, or multi-hop possibly. But there's a tremendous amount of information there. And again, these are observations that occurred even though the annularity was way over here, outside of, far away from where I was receiving. And then for the total solar eclipse, we ran one of these new software-defined radios, which could make these observations on 9 bands at a time. So here's WWV on 20, 15, 10, and 5 megahertz. And here you can see this is 24 hours of data on April 8th, 2024, near Scranton, Pennsylvania. And you can see that at night, the higher bands shut down, the lower bands are strong. We see great traveling ionospheric disturbance signatures going through the night. Here's dawn, and then over here is the eclipse signature. Again, a beautiful S-shaped curve on every band, and you can just see a wisp of 5 megahertz opening up due to the eclipse. I also listened to CHU on 3.33 megahertz, 7.85, and 14.67 megahertz, and you can also see beautiful eclipse signatures there. My friend, so when I got to the University of Scranton, one of the first students I met was this guy named Jonathan Rizzo, and he was a bit of a non-traditional student. And I just caught him at the end of his time as a student there, going for his electrical engineering degree. But really, his life's passion is VLF natural radio. And so for his senior design project, he built this VLF very low frequency receiver that listens up to about a few hundred kilohertz bandwidth, and we installed it in my backyard. It's been running there ever since. And we used that to listen to the naval VLF transmitters that are scattered throughout the United States in places like Hawaii, Maine, Washington State, Puerto Rico, all North Dakota. And again, you can see beautiful eclipse signatures there as well in the VLF network. Rob Robinette, AI6VN, he's back there. He runs the Whisper Demon network, and he has a number of collaborators, Gwyn Griffiths, G3ZIL, who does a lot of his data analysis, and now Paul Elliott, who is, we'll talk about him in a minute. Anyway, Rob has set up this Whisper Demon network, which is an advanced Whisper decoder that it brings some new features to Whisper measurements that aren't present in the normal decoder. So Whisper Demon can measure noise, and the reason that's important is the normal Whisper decoder just measures signal-to-noise ratio. So from that measurement alone, you don't know what the actual signal strength is, you don't know what the actual noise measurement is, you just have a ratio. But since Whisper Demon estimates the actual noise, you can actually back out the signal strength as well. So you can derive the true signal strength from the SNR, and the Whisper Demon system also uses GNSS, GPS-disciplined receivers, so you can actually get proper Doppler shift, Doppler spreading measurements on the FST4W spots. And so here are some examples of their observations from the October eclipse. So here is noise level on 7.04 megahertz on 40 meters. This is out at Rob's very nice receive stations in California, KFS and KPH, absolutely beautiful sites. And so you can see an increase in the noise during the eclipse on 40 meters. Here you can see signal level increases at Ka7OEI for transmissions from WO7I. So here you can see this 80-meter transmission on October 14th. You got an eclipse. You got an increase in the signal strength compared to the non-eclipse days, which are behind it. And then this is a very interesting piece of hardware that you can go see over in the Tapper booth, developed by Paul Elliott. This is a low-power, 1 watt per band, simultaneous, 8-band simultaneous whisper transmitter that's GPS disciplined. And so instead of, it can do transmissions on 8 bands simultaneously, as opposed to scanning through them. And so now you can use, and it's all GPS disciplined. So this serves as a very excellent frequency reference beacon that we can now use and deploy around the world. And here are some examples of the Doppler shift measurements from that on different frequencies. And you can actually see the same sort of eclipse S-shaped curve in these Doppler shift measurements made using FST4W. So another really fascinating project, Steve Serwin, WA5FRF, he's retired from Southwest Research Institute, and he just loves coming up with the most novel ways to use amateur radio to sound the ionosphere. And one of the things he realized is, we can measure the refraction height of the ionosphere by measuring the time of flight, how long it takes a radio signal to get from one station to another, if you know both of the station's locations. But if you're going to make those time of flight measurements, you have to have this GPS disciplined, these oscillators and very accurate time stamping, which is beyond the capabilities of most amateurs. But he realized that if you account for multipath, so if you have a signal be transmitted from one location and it goes both 1 hop and 2 hops, they're going to have different time delays of arrival. And when you add those 2 signals together, you'll actually get a beat note interference pattern on the received signal. And that takes, and you can actually use that beat note timing to back out the reflection of the ionosphere. And so he came up with a waveform that you could transmit over a standard single sideband channel just by feeding it through the microphone port on your regular SSB radio that will send these very short chirps, and you could look for those beat patterns and you can back things out. And so this is some a pre-eclipse test, and so his measurement of height of the F2 region ionosphere is around 250 kilometers, and the red line is the HMF2 height measured by the Austin Ionosonde, which is nearby. And so they ran these for the eclipses. So again, we're just starting to crunch this data. We've barely scratched the surface. So the initial analysis has been performed on a 9-kilometer NVIS and a 317-kilometer regional path in Texas. And the NVIS path was directly within the path of totality. And there was good agreement between the F2 layer height measured by the TDOA analysis and the HMF2 data reported by the Austin Ionosonde. And so you could see height bumps in the F2 layer. They were observed on both paths at times corresponding to the local eclipse passage. And as you look at the more data, you see so much complexity and turbulence in it. And so there's a greater incidence of low, Steve has noticed that there's a greater incidence of low TDOA values suggesting greater E layer involvement than in data sets from previous years. So it's corresponding with the increasing solar cycle. And then we're seeing rapid changing between band conditions observed within the 8-second time span required to send the 10 chirps. And we're doing the analysis, and the analysis has shown the presence of differential Doppler in the different chirp data. And so, again, the data is just, it's lining up really well. So the blue data here is the Ionosonde data. The black data there is his measurement. And they're matching up really well, showing the eclipse refraction height going from, say, 250 kilometers up to 300 kilometers altitude and back down. And so he just has a lot of really nice data showing that. And so we're continuing to work on that. I have another student working on that project with him. We also had the medium wave broadcast, AM broadcast recording experiment. And so this is the idea. It's not, again, not ham radio, but regular AM broadcast radio operates in the medium wave band. And there, at night, these medium wave signals can propagate hundreds to thousands of miles. And because the eclipse is kind of like temporary night, you can see these effects. So Ruth Bamford is a scientist in the UK. She did this during the 1999 United Kingdom's total solar eclipse, and she has a great report. You can read about this. And Nick Hall Patch, VE7DXR, he's coordinating a similar experiment, or he has coordinated a similar experiment for our eclipses, and we've started to get some results in from that. So here's from the October eclipse, and here the KE6EE receiver was listening to KGDD and KKXA AM transmitters north of him, north of his station in California, crossing the eclipse path. And he was also listening to KVEN south of his station, not crossing the eclipse path. All were obscured. And here you can see the KKXA, so that's this station all the way up here. You could see the, you could see the amplitudes measured by his station the day before with no eclipse, and then the day of the annual eclipse, you can see a nice big increase. And then here they were using the Carrier Sleuth software, and they were also able to see the enhancements at night. They were able to see at least on the signal strength rise on the two stations that, because this is the day before where you don't see the increase. Here's where you do see the increase. You only see that increase on the stations that crossed the eclipse path, not on the one that did not cross the eclipse path. So there's so much more to look at. So many people are doing this. So if you want to get involved, you can go to hamsci.org. Now that the eclipses are done, HamSCI is still going strong. We have solar cycle 25. We have solar flares that happen all the time. We had a huge geomagnetic storm that happened last week that I cannot wait to look at the data from. This affects our HF operating, it affects our contesting, it affects our DXing. There's so much we can learn from this. So if you want, come join us. We can show you how to set up a personal space weather station. We can help answer your questions about the science we're doing. You can help us figure out how to make this really useful and interesting to ham radio. So come join us. And I do have to thank all the people who have made this possible. First, of course, the amateur radio community, also the National Science Foundation and NASA and ARDC, and all of the universities, the University of Scranton and my collaborators, Case Western, New Jersey Institute of Technology, Alabama, MIT Haystack, Dartmouth, all of those institutions that are working with us. So stop by our booth in the Hertz building, or booth 5008. Come see our forum today at 3:55 in forum room 2. And thank you very much.